Now, I'm going to do more than is really needed in order to get my solenoid to infinity. I'm going to try to describe the entire behavior at infinity, solenoids and everything else included. This is not the most effective way of getting at the solenoids themselves. It's not the fastest way. But it's really intended also, and it's an example of infinitely many blowups, and how infinitely many blowups can be used to analyze the behavior of rational functions near points of indeterminacy. If you think, well, let me give you a rough description of how the dynamics of such a map look. In crudest outline, a Hamel map looks like this. That means that there is a region V plus where x is greater or equal than y, and x is z, and x is greater or equal than some number r, such that h of v plus is contained in v plus. And if you think about the formula, you will see that this is essentially obvious. If x is large and large as compared to y, then this p of x is by far the dominant term. So this will be even more true next time. And points in this region will march off to infinity. There's a formula for h inverse. H inverse of xy is equal to y d of y minus x over a. And the consequence of this is that the set v minus, which is described by similar inequalities, is invariant under H inverse. In particular, all of the really interesting dynamics is happening inside here. So that if I make the definitions, remember these definitions are, the terminology is directly inspired by the terminology for polynomials in one variable. In one variable, let me just write this someplace on the side. The basic object is if you had a polynomial with z, then k sub p is a set of z such that p iterated n times of z is bounded as n tends to infinity. You can't quite hope to make the same sorts of things here, or rather you can, but you can't ignore the fact that h is invertible, and that therefore you must think in both directions. So you have a set k plus is equal to the set of xy, or maybe I'll say a little bit of space. This is a set of xy such that h iterated n times of xy in norm is bounded as n tends to plus or minus infinity. And it's more or less obvious from this description that k minus has to live somehow in here, and k plus has to live in there. And k, the object of real interest, is k plus interk is where all the really recurrent dynamics lives.
So the R is only the positive when you suppose two axes don't go.
They're labeled absolute value of x and absolute value of y, and you should think of this picture as a caricature.
Right. So everything lives over.
Everything is four-dimensional, living above this, and in no sense is this actually a quotient of the dynamics. I mean, it's a caricature. Very reductionist. Now, the idea about k plus and k minus is that we're going to creep up on k from the outside, just as for one-dimensional polynomials, we crept up on polynomials from the outside using the conformal mapping of the complement give, and hoping to go to the boundary of this conformal mapping, to give us names for points on the boundaries of KP. But we're going to try to do the same thing. It isn't quite a word, but it's going to come close. But one thing that has to happen as a result is that one has to really understand what it is that's happening at the figure. So the discussion that comes at this point is to try to extend the Hemel map to infinity. Well, there's an obvious way of doing it, which is to try to extend it to the projective plane. And here is a drawing of the projective plane. This is the x-axis, this is the y-axis, and this is the line in infinity. Now, it is almost obvious again from this description that what the Hemel map actually does in the projective plane is that it collapses the entire line in infinity to this point. And it has a point of indeterminacy here. Now, the object of this talk is to tell you that hidden in this point of indeterminacy is a solid line. That in some appropriate sense, if you take the dynamic blowup of this point, the dynamic blowup of this point is a solid line. And I hope to make this absolutely precise before I'm through. That's the main thing. The process that I have found in order to try to understand this is two steps. One step is to perform complex blowups, to try seeing more and more of the structure in the complex. But then there's a second step. The complex object that's created is very nice, except at 2 points where it's absolutely horrible. And to try to understand what's happening at the absolutely horrible points, you need to do a further new kind of blow-up, in which you start thinking of complex curves in a complex surface as real surfaces in a real four-dimensional object. And then you can blow them up again in real algebraic geometry. And the second blow-up is the one which creates the solid lines. Now, I would like to take one... Excuse me?
How many solenoids are we to expect?
You're going to expect two solenoids, one hidden here, but there's another one hidden here also, because the Hemel map itself being bijective, when I want to create an intelligent compactification of C2 to which the Hemel map extends, I'm going to want that one also to be bijective. And then I won't be able to get around with just collapsing things, and I'll construct a solenoid here also.
So intuitively, we should think of a repelling solenoid and a tracking solenoid?
Yes, there will be a repelling solenoid and a tracking solenoid. In fact, maybe I can give you just as earlier motivation a picture of what kind of object I'm talking about. So, contemplate this. If this came out right, it's a picture of two tori in R3 that link with linking number 2. And you should be able to imagine that if the z-axis is coming out of the orb this way, the rotation by 90 degrees sends torus 0 to torus 1. Now, I want to manufacture the following map for the piece here. The map in question is first rotation by pi over 2 around the z-axis, composed with reflection with respect to t0. Now we have to understand carefully what I mean by reflection with respect to t0. T0 is, by itself, independent of T1, is an unknotted torus in S3. Being an unknotted torus in S3, there exists a map which makes the outside of the inside and the inside of the outside. Of course, the word reflection isn't very well chosen because it's very far from being the identity on the boundary. On the boundary, what it does is it reverses the two generators of the homology. It exchanges the generators of the homology group. And the easiest way of writing such a map is to think of the Z-sphere as the set of Z1, Z2 in C2 with Z1 squared plus Z2 squared equals 1. And then to let the reflection, you have a torus, T is the locus here, Z1 equals Z2 equals 1 over the square root of 2. Obviously, this is a torus because both Z1 and Z2 have an argument, and so it's a product of the circle with itself. And then you have the map Z1, Z2 maps to Z2, Z1, which evidently turns the inside, where Z1 is bigger, to the outside, where Z1 is smaller, or something. So, given an unknotted torus in S3, you can turn S3 inside out, mapping the inside to the outside, and that's what I mean by this map. This map is, of course, only defined on the 3-sphere. It's not defined on R3. There has to be a point inside T0 to send to infinity, and a point at infinity has to go to some point inside T0. I am not claiming that this map is quite well defined by what I've said. There are choices involved in making rho T0, and the choices do affect the conjugacy class. Now, the question I want to ask is, where does T0 go? Well, under the rotation, T0 goes to T1, which is completely outside of T0. And then under the reflection, it gets reflected back completely inside T0. So T0 is mapped into itself. Okay, T0 is mapped to T1, and T1 intersects this disk in two little circles. Once I do this reflection, this disk gets turned into a disk like that, and these two little circles become two circles like this. In other words, the image of T0 goes through T0 locally in two tubes like this. And no doubt you will immediately see that the moral of the story is that this map maps T0 to itself. In the standard solenoidal way. And notice that the inverse map maps T1 into T1. As a result, there's also a solenoid sitting inside T1.
Degree 2 torus.
Excuse me?
Degree 2 torus. He says a solenoid. He says solenoid.
Well, so no, T0 is mapped into T0 as a degree 2 torus. You're absolutely right. What I mean is at the intersection of the forward images. So there's an intersection, there's a sigma plus is equal to the intersection of F, this is F, F to the nth of T0. And then there's a sigma minus, which is equal to the intersection of F to the minus n of T1. It could be T0 also. It doesn't really make any difference. They are in the standard such a disk is, I'm sure that you have all seen this picture many times before. The first time you see the two disks of intersection, and then when you do it next time, you see two more in each one of those, and when you do it next time, you see two more inside each one of those. So that this sigma plus as well as the sigma minus end up being fiber bundles of Cantor sets sitting above a circle. And this fiber bundle is completely non-trivial in the sense that if you grab one point of this solid and follow it around, well, if you follow it around once, you end up in the other one of these two. But if you follow it around twice, and you started in this one, then you'll be in that one, and so forth. And however many times you go around, you're never going to come back to where you started. Now, so what I have described here is a linked solenoid mapping in a language which was forced on me by Smiley, who told me that I couldn't call them solenoidal mappings because he had already adopted the word for something else. So they're linked solenoid mappings. They're mappings from the three-sphere to itself, which have two invariant solenoids, one attracting and one repelling. And all of the ambient space is filled with a collection of tori, nested, but nested in this 2-to-1 way, down in one direction, going down towards one of the solenoids, and nested in the other direction, out towards the other solenoid. It's not really obvious that there exists math from the three-sphere to the three-sphere with two invariant solenoids like this, but it is true, and it's even possible to just write formulas for it. And my claim is that what's happening in infinity for a pinhole map is this. So my eventual object is going to be to glue on a three-sphere of infinity to C2. Of course, this three-sphere is not going to be glued on in the standard way by just adding a point at the end of every ray. It's going to be a lot more subtle than that, and some points are going to be explored really carefully, and other points are going to be just glued on in that way.
But topologically, you're just gluing a three-sphere on?
Topologically, I'm just building a 4-ball by gluing a three-sphere onto C2 in the most obvious way, so that the pinhole map extends and the restrict continuously, and so that the extension looks like that. So sitting out here, there's going to be one solenoid, and sitting out there, there's going to be another solenoid, but actually K plus is going to have as its closure the repelling solenoid, and K minus is going to have as its closure the attracting solenoid. The sphere is going to be a real pro-semi-algebraic object. In the sense that in its intrinsic structure, it's going to be an algebraic surface with corners. And along the solenoids, the corners are going to accumulate. That's what its natural structure is. I don't think it has any natural smooth structure or anything actually much nicer than this.
What would that be?
The map will be pro-algebraic, every bit as much as the space is pro-algebraic, and it will map angles to angles. It will map corners to corners and be smooth as can be in the intermediate parts. You should think that this is probably more like the 3L world than like the smooth world. Excuse me?
What does scroll mean?
Pro means projective limit of, or perhaps inverse limit of. So pro-algebraic means projective limit of algebraic varieties. At one time back in the 60s, they were big things. And they seem to have sort of faded. Okay. So the first step now is to try to get my Hidden map well defined. Now let me make one little bit of statistics. How many people are comfortable with my using the word blowup? Gosh, that's a pretty small minority. What? If I just start talking about you blow up the surface at this point, how many people are going to know what I'm talking about? These are the most ordinary variety of blow-ups, points in surfaces.
Just say what it is.
Okay. Okay, so
How do you feel like it?
that was my question, whether I needed to give a definition or not. And the answer is yes. So the case to try to remember is that blowing up C tilde 0, C2 tilde 0, blowing up the origin, that's 0, blowing up the origin in C2. This is the set of pairs of XL in C2 cross P1, such that X belongs to L. L is an element of P1, so it's a line through the origin. And notice that this object projects to C2 by just mapping XL to X. And the inverse image of all points except the origin are just a single point. Because if you know a point which is not the origin, then you know the line from the origin in that point. So L is determined by X, unless X is the origin. And then all lines go to the origin. So what has happened when I make this blow up is that the points have remained the same, except for the origin, which has become a line. Now, there's a very nice way of describing this, which is thinking that it is the equation. It's sitting, this is not quite true. It's sitting in C2 cross C, given by the very pleasantly said equation y equals zx. You see, for every fixed z, there is a line that slopes z. And the point xy is on the line that slopes z. That's what it's saying that it satisfies this equation. So you can think of it from that point of view. I will draw it in R3, but the underlying picture is exactly the same. You have the line that slopes 0 at height 0, and then you get lines turning at height z using the line of slope z. Now, the only problem with this is that we are missing the points on the vertical line. You have to take two copies of this and glue them together, because I did not get the points which were on the vertical line. They don't satisfy this for any value. But there is something important to understand, which is that the picture which is absolutely wrong is this one. Here is the surface, and one point has been replaced by a line. That's completely wrong, because this line is completely non-singular. There's nothing bizarre about it. It's really the z-axis here, together with the point of infinity corresponding to the vertical direction. But the blow-up is a perfectly good smooth surface given by this equation. The operation of blowing up is something that we will see in a somewhat more complicated setting in the future, where you can actually blow up not just points and surfaces, but you can blow up arbitrarily sub anything to anything. And the process becomes more complicated. But this will be enough for temporary. Now, this really means, when you do this blow up, that you have replaced a point by a refined point, where you have a point together with a specific way of approaching it. This point here might correspond back in the original C2 to approaching the origin along a particular line in some particular direction. this sequence is convergent to the blow-up, whereas this sequence is not convergent to the blow-up, even though it's getting close to zero, because there's no limiting slope to how you're approaching zero. If you have a point of indeterminacy, you might reasonably expect that it might be removed by blowing up. Because if you blow up the point, then a sequence converging to a point of blow-up is approaching this point in some particular way, and even if there's no limit generally, well, there might well be a limit along specific lines. That's not the case. But there is some sequence of blow-ups at this point, which will make the map well-defined. And I'm going to try to give you a drawing theoretic way of understanding the sequence of blow-ups. Doing the algebra is extremely unenlightened, though it's the kind of thing which algebraic geometers do for breakfast on a regular basis. I mean, you shouldn't think that there's anything actually hard on this. Algebraic geometers view all of this as totally elementary. So my description of how to do this is going to go along the following lines. At the moment, nothing maps the points of it. Nothing maps the line at infinity. And obviously, once the map becomes well-defined at this point, something will have to map to the line at infinity. Well,
you're starting out, so you have a map on C2.
I have a map on C2.
That's all you have.
Well, actually, it's well-defined in P2 also.
Yes.
Yeah. Polynomial. And
let it go.
So if you pin out to a line, the line of infinity, the image of such a line is a parabola, and the entire line, the map is well defined in the line of infinity, except at that point. But it collapses the line of infinity. However you head out, the image is going to become a parabola, which is going to head toward this point in projector space. So here is my question. It's easy to figure out what ought to map to the line of infinity. Namely, I have a formula for the inverse, so I can look at the inverse of the line y equals mx. What? I can find the image of the line at y equals mx. And as it turns out, that's a collection of parabolas which come in to this point. They are cubically tangent among themselves and quadratically tangent, that is, ordinarily tangent to the line of infinity.
What is that collection of parabolas?
So you look at the inverse images of these lines.
Oh, the inverse images.
You look at the inverse images of those lines, which you can perfectly easily compute because I have a formula. And you discover that it's a collection of parabolas which come to the point of indeterminacy. So what I'm saying is, if you approach the point of infinity along one of these parabolas, then the image will be willing to tend towards a specific point of the line of infinity. Okay, so the sequence of blow-ups that I need to make in order to make the map well-defined here has to pull these parabolas apart. Okay, so let's do it. If I blow up this point becomes a line. These parabolas are going to become curves that are going to tend to this point. They are going to, the points of this line correspond to slopes of lines to this point. And in particular, these ones have the same slope as the line of infinity. So these parabolas are going to tend to this point. But something has been improved. They were ordinarily tangent to the line of infinity. Now they're not going to be tangent to the line of infinity at all. They're just going to go right through. But they were cubically tangent to each other. So blowing up reduces the order of contact by 1. And they are going to become ordinarily tangent to each other. Gosh, this color doesn't look any different from white. This one should. So they are now going to be ordinarily tangent to each other. Well, I haven't pulled them apart. So I make one more blow up. There's the line that has replaced this. These things are all tangent to each other, so they have some direction. That direction is some point at this line. They were ordinarily tangent. They're not going to be tangent at all. They're just going to go through different slopes. One more blow up. That's what blow-ups are for. They pull things apart. One more blow-up. And they will look like this. They now have been pulled apart. Excuse me?
You didn't draw enough blow-ups.
Yes, I did. This is the new line. Now, there's an extra line here. There's an extra line here. Yes, I have.
Both are handoffs. If one of them should be.
That may be, but there's an extra line that you don't. This line is a line that you don't see. This line is the new exceptional divisor. And these yellow lines that go through are the yellow lines that were here.
Whoops. This vertical line is line, the yellow line is infinity.
This vertical line is the proper transform in the language, but yes, going through here corresponds exactly back in the original picture to going here. And there is now a perfectly well-defined map from this thing, I made the blow-ups, and this map maps this line to the line that was designed for this purpose. And all the remainder of these three lines are still being collapsed here. So let me call this map, this space, X. And you have a perfectly good map from X to P1, which perhaps I will call P2, which I will call H2. Now, if I were an algebraic geometer, I'd be perfectly happy. I would have resolved my singularity. But since I do dynamical systems, I'm not happy at all. Because this is not a dynamical system. The domain and the range are completely different. And I can't iterate. So the next stage, well, there are various ways of saying it. One way of saying it is that there's a point in this picture which maps to the previous point of indeterminacy, and I can blow that one up again, and then I can look at the new point of indeterminacy and blow it up again, and so forth and so on, and take the projected limit of all these blow-ups. I'm going to do something slightly different. I'm going to speak about x infinity is equal to the subset of x to the z. The set of sequences of point in x, of point in x, of point in x, and so forth, such that xn plus 1 lives in the graph of h tilde. Or perhaps the graph of h. And then I'm going to take the closure. Let me see. So let me let gamma in h cross a, in x cross x, is the closure of the graph of h, and then x infinity is equal to the set of sequences No, the graph of H actually lives in C2 cross C2, which is contained in X cross X. And then I just make its closure with X cross X. Okay, the closure, the graph of H lives in C2 cross C2, which is a subset of X cross X. What? You will. You will get something with horrible singularities infinitely named vector, which can be understood as a blowdown of the one I'm about to create with infinitely many blowdowns. Yes, there are good reasons for which this one is much nicer than the one that you get if you start with just CP2. Now, this space X infinity, of course, I mean, it's a projective limit. It's a subset of an infinite product. Is it any sort of civilized space? Well, one thing that one can say is that C2 is sitting inside X infinity. And if you put the shift here and the Helmholtz out here, this diagram can use. Now, why is C2 sitting inside X infinity? Well, if X naught is actually C2, then its entire forward image and its entire backwards image are entirely determined by this condition, since within C2, H and H inverse are actual maps. So you just take X naught, H of X naught, H2 of X naught, and H inverse of X naught. And so forth. That is how C2 is embedded in X infinity. What is sitting in infinity? So I claim that what is sitting in infinity is a divisor which looks like this. Your old line of infinity is here. So that's there's the line of infinity. C2 is sitting out here. And that is sitting in infinity. And in particular, at infinity, there are two horrible bad points. The two horrible bad points corresponding, I guess the board I was thinking down is this one. If I decide to call this point here,
X infinity is compact, right?
X infinity is compact. It's a product. It's a closed subset of a product of compact spaces.
So the infinite thing has to converge.
Yeah, the infinite thing has to converge to something. So let me call these two points P and Q. This point here, let me see, I really well, this point here is the point P, 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 and this point is the point Q, Q, Q.
So this thing doesn't accumulate on itself, it only accumulates to these.
Yes, it doesn't accumulate as stuff, it only accumulates to these points. Excuse me?
What were P and Q?
Let me, they're points of X. They're points of X. And Q, P is the point which maps to there. And Q is this point which was there all along. And what you can do, a typical sequence in this space is P, 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 P lots of times. And then someplace in the divisor infinity, and then Q, 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 Q. Except that it might be P, 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 P lots of times, and at some point of this line, after which it can be some point of this line, after which it is Q, 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 Q. Those are the only kinds of sequences that there are.
Where?
In X infinity. Which are not in C2. You have the sequences in C2, and then you have the sequences which live in infinity. And those are Q, P, perhaps forever, but if not forever, then at some point you have to leave it. You can leave it to anywhere in all of this. But if you happen to leave it to here, then you get one more hop before you're at Q. Otherwise, if you happen to go to here, then you go to Q in one fell swoop and you're done. Wherever you are, at the move when you aren't doing it, when you aren't, at the move where you aren't at P or Q, that determines where along this line you are. And the shift on this infinite divisor corresponds to the, extends the Himmel map within your C2. Now, in this part, yep, this point shifts to there, this shifts to there, and so on.
What you were saying, all of it, they're all PDCs and then a couple of things that you do.
Yes?
It's not consistent.
Yes, it is. Supposing that you take P, and you take one more P, then you put whatever you have, and then you continue. That's having done the Himmel map once to your... these things, they're labeled by the index on which you're not P or Q. You're not P or Q. And if you do the Himmel map once, you get the index.
The first description was the map on X infinity, and the second was the natural.
Yes.
You got a shift. You have a word discussion. I don't see how that.
So the key point is that xi plus 1 is in the graph. In other words, roughly speaking, xi plus 1 is h of xi. And that is exactly true when you're in C2.
Yeah.
In other words, doing the shift is like doing the Himmel map, and that is actually literally true within C2, which is saying this diagram tweaks. Now, at infinity, you also have to understand what kinds of sequences you can get. Is it this picture you want to look at?
Yeah, right. Isn't that part of this X infinity? Oh, only some pieces of this is an X infinity.
No, it is not. Yes, this is an X infinity, absolutely. So here you might have the sequences which are P, 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 P in the 0th position.
Oh. Right, so that's a picture of sequences.
0th position, a point of L infinity. And actually, in the minus first position, you might have a point of the thing that maps their line of infinity.
Yeah.
Okay, now this thing here is a set of things which in 1st position are in the line of infinity. And in 0th position we're in the preimage of the line of infinity, and so forth. In fact, these lines are the transitions, the things which twice are not P or Q. And then the other parts are the ones which are not P or Q exactly once. Okay, now, this space is almost an object of algebraic geometry. It's almost an object of algebraic geometry, except that these points are extremely unpleasant from the point of view of algebraic geometry. For instance, they have the property that every neighborhood has a second homology group which is infinite dimensional. Because you take any neighborhood of them, well, they're going to contain infinitely many of these complex lines, which will give you, each one of which will give you a generator for the second dimensional homology. So the object is to, in some sense, compactify. I've in some sense compactified C2 in a way which is compatible with the dynamics. But the problem is that the space by which it's being compactified is not nice. It's fairly nice. But my claim is that hidden inside these points are solid points. So that requires a bit of explanation. And I think I'm going to try some slightly handwritten description of how one resolves these points. There is a more or less obvious space, B, X, N, M, which means I'm going to take the sequences, but I'm going to take the sequences only Xn, dot, 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 Xn. With the consistency condition written up there about successive points. This is an algebraic variety at every stage. And it consists of kind of chopping this off someplace and chopping this off someplace at the other. Then I'm going to define X infinity maps to X and M. If you get N and M get bigger, the ones which are bigger collapse down to the smaller ones. But in the opposite direction, you have to remove some points. If you want to map from a smaller one to a bigger one, you're going to have points of indeterminacy that you're going to have to take out. Those are the points that are being blown up. You're trying to map backwards to a blow up. And that doesn't quite exist.
So there's a normal map, a bigger interval to a smaller interval.
Yeah. From a bigger interval to a smaller interval, all the way from X infinity to X n m, there's a collapsing map. But in the opposite direction, there's not quite a map. It's onto. It's onto, yes. So I want to define the oriented real blowup of X minus n to n with respect to the divisor at D minus n, the divisor at infinity, and then take the projected limit as n tends to infinity of these things. And let me try now to tell you what I'm talking about. This is the space X and F that I was talking about, and the divisor is the part of infinity. So this is a four-dimensional object, that's a two-dimensional object.
What's that B?
That means stands for real oriented blowup. And what I mean by real oriented blowup, I think rather than trying to write down a rigorous definition, roughly speaking, I'm going to do polar coordinates. So when I see a line in a plane, I'm going to open up that line so that every point becomes a circle. In other words, it's like when I'm looking at outside and I'm going to remember the polar angle at which I'm approaching points of the line.
Like cutting away a small tube.
It's like cutting away a small tube. You really should think that you're going to get inside the thing and blow it up.
Too small.
Blow it up into a little something. Then I'm going to take the projected limits of these things after having blown up all these devices.
Well, that corrects.
What?
That corrects the dots.
That corrects the dots.
Good.
That corrects the dots, exactly. Now, one thing is, what is the global structure of this thing going to be? And, excuse me? That is the locus of infinity, divisor. This is D infinity. D infinity is the part of infinity with respect to C2. And D minus n is correspondingly the part of infinity. So it contains the divisor, but only between some minus n and n.
So the final set of two straight intersections, like you said.
It's a finite set of two spheres. It's a finite set, just like this. It's exactly just like this. Some have two distinguished points on them where they intersect others, and others have three, and others have one. For one thing, independent of n, the total space of this is always the same. As Dennis was saying, a good way of thinking about this is taking a little tubular neighborhood of the divisor and trying to see what you're seeing in the boundary of this tubular neighborhood. But if you're going to do blowups on the inside, that's not going to change the structure of the tubular neighborhood. Now, nothing could be easier than taking a tubular neighborhood of the line at infinity. A tubular neighborhood of the line at infinity is obtained by taking a big sphere and looking at what's outside of it. Taking a big ball and looking what's outside of it. So here's the neighborhood of the line at infinity. And the boundary of this object is always going to be this 3-sphere. That 3-sphere is the boundary forever, however many blowups I do. It's always homeomorphic to that. Yeah, it's going to get crinkled. It's going to get crinkled, but it's always going to be that as a space. Now, before any blowups, what structure does it have? It projects onto the line in infinity, the way the boundary of the tubular neighborhood always projects onto whatever it's a tubular neighborhood of. And the inverse images of points or circles. And this is our old friend, the Hopf vibration of the 3-sphere over the 2-sphere. So this 3-sphere naturally comes in the most standard way. X, Y maps to the point with homogeneous coordinates x, y. Maps as a 3-sphere to a 2-sphere, a 5 ring pi surface. What is going to happen to this structure as I start blowing up points? Well, let me start making the drawing. Here is a drawing of the 3-sphere with the Hopf vibration formula. So what do I mean by the Hopf vibration? Crossing it. In the Hopf vibration, the fibers are circles linking with linking number 1, and I've drawn 2 of the fibers. This particular fiber corresponds to this point. It's the fiber above this point. What happens when you blow this point up? In other words, when you go to this stage of blowups, is you replace this circle with a little torus. The torus itself, the boundary of the torus, being the inverse image of this double point. And what I really have to tell you is what circles are fibering the complement. Well, on the outside, you still have the old circles of the Hopf vibration. And on the inside, you have just the circles that run around. There's a precise sense in which one can understand this, but temporarily try to get the picture. Trying to make it precise is actually not good.
I don't have a picture of what you're saying. Say again the picture.
So,
What are you describing?
here's the 3-sphere. This 3-sphere, that one there, is now sitting here. It projects onto whatever it is the boundary of the tubular neighborhood of. And of particular interest in this 3-sphere is the inverse image of this point, this double point. My claim is that that's a torus. This is a torus decomposing the 3-sphere into 2 pieces. And these 2 pieces are the parts which project onto here. The outside is foliated by circles still by vibration, and the inside is foliated just by curves running around like this. And there's a reason for which those are why the curves.
These foliations do not fit together.
They do not fit together. Coming from the inside and coming from the outside gives you a basis for homology. They cross. Yes, exactly. Okay, now, what happens when I want to go to this picture? Just as here I had blown up an ordinary point, so I had to thicken the corresponding circle. Here I'm blowing up a double point, so I have to thicken the corresponding torus. So in my next picture, I'm going to have two tori. The old torus was in between these. The inside of this is still foliated just like the inside of this. The outside of that is still foliated just like the outside of that. And in the part in between, as Dennis was telling me, I had two directions, so I can take their sum in the homology. And I foliate the inside here by the sum. But think a little. The outside is foliated by circles of type 1, 1 with respect to the obvious homology basis. The inside here is foliated by curves of type 1, 0. And the sum of the two is 2, 1. This part in here is foliated by circles of type 2, 1. Circles of type 2, 1 are not quite torus knots, but almost. They go around twice like this. So when I make the next blow-up, which is at an ordinary point of the region between the two tori, what I'm going to have to take is this 2, 1 circle, thicken it to a little torus, and put an foliation on the inside. Now you should see where the solenoid is coming from, because my map is going to map the outside of the bigger torus into the outside of the little torus. In other words,
generally, you take a region that's foliated, come
yes.
out with a tube around it, and change the foliation inside.
Exactly. Well, I mean, either you thicken the torus, or depending on whether you're blowing up a double point or a simple point, you either thicken the torus or thicken the curve. Thicken it up a little bit, and then there's a rule for telling you how to build the new foliation inside in the new region you create. Okay. So this object is what you get from my solenoidal map. If you iterate it n times, or perhaps 2n times, and then you take the projected limit, you're going to get the full structure of two solenoids, one attracting and one repelling, and the mapping tori down from one level down to the next level.
What are these circles? In terms of this structure, these are circles that blow up. These are circles that are created by blow up.
Yeah. Well, it's especially the tori. No, the circles are created too. But I find it easier to think about the.
So there's something that each point becomes a circle. So each point is blown up as a circle.
Yes. Yeah.
And you're describing the circle.
Yes. So in this picture, all the ordinary points became circles. All the double points became tori. And the two bad points became solenoids. It's a special kind of blow-up, okay, the real-oriented blow-up, which allows one to resolve this sort of singularity into spaces which, well, I don't know, I mean, a solenoid is a fairly nasty object, but still not that bad. It's incomparably better than just saying that it's something mysterious and incompetent. sort of over here is some extremely long thing approximating a solenoid. And then you take one which is over there, a much longer one approximating a solenoid better is that. Okay, so now I really am out of time. And it's too bad because I was proposing to show pictures. But let me just show at least one or two pictures, just one or two pictures.
Yeah.
What?
That's 4 lives.
I have 4 lines. That's hello, computer. Well, maybe I should respect Dennis's view that I have 4 lives and reserve the showing of the pictures. Well, let me show you the pictures. Oh, that's not such an interesting one. But it'll do. No, that's not really very good. Let me take someone like over here. And then let me do, oh, that's a really very nice one, actually. And let me do this. Now, this is a picture of something which is sitting inside K minus. It's sitting inside K minus. And as you go out here, you're going out to the solenoid. You're going out to the solenoid, and in fact, because this is a picture of an unstable manifold, you're going to a particular part of the solenoid, which is, so a solenoid is something where you can write things as epsilon 1, epsilon 2, epsilon 3, epsilon naught, epsilon minus 1, epsilon minus 2, and so forth. With the epsilon I equals 0 or 1. You can write them as just infinite binary expansions, bi-infinite binary expansions. Except that to the right you have the ordinary requirement that point 1000 is the same thing as point 01111. You have the ordinary identifications. And to the left you have no identifications, and nobody tells you that it has to end with zeros or ones. That's one of the possible descriptions of the solenoid, and a very nice one. It's just your ordinary numbers, except that you don't stop your digits to the left. Instead of all being all zeros to the left, they can just be anything. Sitting inside the solenoid are the real numbers. You can end up with all zeros. Actually, you also have to think a little bit about ending up with all ones. The ones which end up with all ones correspond to the negative reals, and the ones which end up with all zeros correspond to the positive reals. So, sitting inside the solenoid are the reals. And the reals are what you see here. 0, 1, 2, minus 1, minus 2, minus 3. You are really seeing out of infinity in this unstable manifold, the Hemel manifold. You are seeing the real path component of the solenoid. The solenoid is connected, but it still has path components. That's the numbers like that. And in particular, you can read off the digits in base 2. If you want to come down here, well, in one direction, you're going to have 0, 1, 0, 1, 0, 1. And in the other direction, you're going to have 1. And eventually, you're going to have all zeros, because we're in the positive part. Down here, eventually, you have all ones. Eventually, you'll be all red, maybe by the next stage already. And this interaction of the solenoid at infinity with its binary decomposition and so forth, and leading to paths down to the black locus, which is K, gives you a way of trying to creep up on this mysterious K at finite distance from the non-mysterious solenoid at infinity, giving names to the dots, this point here being V dot with name 1/3 perhaps and so forth, is the best hope that I have for giving a complete description